Well, symmetry is something we're all kind of very familiar with, actually, intuitively. Symmetry is something we naturally kind of are drawn towards, not just mathematically, just visually. So, symmetric can mean many different things, but for example, things which have reflective symmetry. So, if you have some sort of shape, and if I reflect it in a line, it stays the same. Something like an equilateral triangle, right? If you draw a straight line through the center and one of the vertices, and you reflect it across that line, it stays exactly the same. So our minds are very drawn to symmetry. It's very appealing to us, it seems to be anyway. So let's think about what symmetry would mean in the context of functions. Well, it makes sense to talk about symmetry from the perspective of graphs because that's a really good way to visualize what a function is doing. And let me show you two types of symmetry that seem worth thinking about. So examples. So again, let's draw two graphs. Of potential functions. Okay, so let's take one graph that has a certain type of symmetry as follows. So forgive me while I try to do this. It's not that easy to do it completely by hand. Failed already. That's good enough. So that's a graph, and it has a certain type of symmetry, doesn't it? Right? So if you take this graph and you reflect it across the x-axis, so it's the same after we reflect it across the x-axis. Did I say the x-axis? I meant the y-axis. Forgive me. So that means if I reflect across this, it's totally identical. Okay, so that's one nice kind of form of symmetry that a graph can have. Very powerful. Another form of symmetry would be where I would take some sort of graph and I could rotate it by 180 degrees, or pi in radians, 180 degrees around the origin, and it would still look the same. So that would be something along these lines. So if I take now something that looks like this. So this one's not so easy to draw either. So imagine if I rotate this around. If I rotate this around the x-axis like this. Or maybe I should say rotate it around the origin. Apologies. Okay, so this now is the same after, as I said, rotation. So it's a different kind of symmetry if you want. Same after rotating by 180 degrees around origin. So around 0, 0. So I take this and I rotate it around, it's exactly the same. Okay. So what I want to do is to single out what this means really precisely. So the first situation, if a graph has that property, so if you have a function and if it's completely symmetric when I reflect it in the y-axis, we're going to call this situation even, or we're going to say the function is even. In the second case, if after rotating around by 180 degrees around the origin. If you're exactly the same, we're going to call this odd. So it's kind of strange terminology, like why would you call this even and why would you call it odd? I'll talk about that in a little second. We want to really pin down what this means precisely, right? We've got a graph which gives us a good feeling for what it is, but we need to kind of really work out a precise statement. So let's have a think about the first case, shall we? So imagine I have an input here, x. Okay, so that would correspond to what? An output over here, f of x. Now, I have this reflective symmetry across the y-axis. So if I take the point on the opposite side here, minus x, and I go through exactly the same procedure, it has to be exactly the same height. So it's not perfect here, as you can see. Mostly just because of my bad drawing skills. Come on. Okay, we're going to have to... So if this was done correctly, it should be complete match-up. Like I said, it's a bit of a pain to draw. But what do I have? Well, now this point would correspond to f of minus x, wouldn't it? I know that's terribly small, but it's f of minus x. So what can I see? Well, in this case, f of x and f of minus x have to be exactly the same. Right, they have to perfectly match up. So that seems to be a crisp way of describing this symmetry. So let's do it. Definition. Definition. So we say that f, the function, is an even function. Not to be confused with an even number or anything like that. It's an even function if f of x, or f of minus x, is equal to f of x for all x in the domain. So it's a global property. Okay, real crisp. What about the second example? Well, let's do the same thing. In the second example, so if I take, I don't know, some position here, let's say x. So that corresponds to this point here. So I would get f of x over here, wouldn't I? But now if I was to take minus it, so minus x over here, well, that would correspond to this position over here, which would be f of minus x. And notice, because of this rotation, these are negatives of each other. So f of minus x is minus f of x. So in this specific instance, we could capture this using that fact. So we say that f is odd if f of minus x is minus f of x. It's kind of weird. It's like you could take the negative out the front. You're not really doing that. It's just a property, right? So this is for all x in the domain. Again. So an even function, intuitively, if you were to graph it, the graph has reflective symmetry across the y-axis. Precisely, it's the statement that f of minus x is equal to f of x for any x in the domain. An odd function, intuitively, it's the statement that if you rotate the graph around the origin by 180 degrees, it preserves it. So it's got rotational symmetry if you want. Then a precise statement is the statement that f of minus x is minus f of x for any choice of x in the domain. So, interesting. I would imagine you've seen odd and even functions before, but probably only from the perspective of polynomials. So this is a good example of when you learn things in high school, it can be simplified in ways that aren't really explained to you. So this is a very general property. And this is a very general property. This is a statement that could apply to all sorts of different functions. They don't need to correspond to, well, polynomial expressions in X. So let's do a few examples though, right? So examples. All right, so let's do f of x. Let's have it as a polynomial expression, x squared plus 1. Now, is this odd or even, or is it neither? It's pretty special being odd or even because you need to have these very strong symmetry properties. The vast majority of functions are not going to satisfy these properties at all. But are you odd or even? So this now is one of these important things to understand about university mathematics. If you want to check if something's true, like is it odd or even, you must check the defining property. The defining property is that one of these two has to occur. So either you show one of those two happens or you show neither of them occur, probably by selecting a specific point where it fails. But let's do this one. So let's see what happens. The departure point is always the same. Let's just see what happens when I feed in minus x. So I feed in minus x, it's minus x squared plus 1. But minus x squared is the same thing as x squared because minus 1 times minus 1 is 1. So this is equal to x squared plus 1. This is equal to f of x. That's true for absolutely any x at all in the domain. That's all numbers. Brilliant. So this tells you f is an even function. So I'll write it like that, even function. Let's do another one. Let's do f of x is equal to x to the 5, I don't know, plus 1 over x. So let's go through the same procedure. Let's not second guess anything. Let's do f of minus x is equal to, okay, so it's minus x to the 5 plus 1 over minus x. So what's this equal to? This now is equal to, well, it's just minus x to the 5 with the minus outside. So maybe like this if you want to write it like that. Then what? Well, the negative can come at the front, minus 1 over x here. So putting all this together would give you minus, by the distributive property, minus of x plus 5, x to the power 5, sorry, plus 1 over x. Notice what this is. This is exactly minus f of x. And that's true of any x in the domain at all. The domain here is all things which are non-zero, because you can't divide through by 0, but it works completely fine for every single one of those. So what's the conclusion? F is an odd function. F is an odd function. Right, something to observe here. These two functions are sums of powers of x. And in the first case, all the powers are even. So in particular, notice this guy, it's 1, sure, but it's actually x to the 0. And 0 is an even number. So all exponents are even numbers. Even numbers. So an even number is one that's divisible by 2. 0 is even because 2 times 0 is equal to 0. Well, here, x, 1 over x is equal to x to the minus 1. And minus 1 and 5 are both odd numbers because they're not divisible by 2. So all exponents are odd numbers. But numbers, right? So this actually really is where the terminology comes from, essentially. Because if you have x to some power, some integer power, it'll be an odd or even function if and only if the exponent is an odd or an even number. But it's a much broader concept than that. And I should say, it's not the degree here that matters. It's not the top power. It's not the top power. It's every power. So as a warning here, because this is a classic misunderstanding. Odd, well, even stroke odd polynomials so the first is a polynomial. The second example here isn't because I've got a negative power. Polynomials have positive powers or non-negative powers. This is not the same this is not the same thing as just saying the degree is odd or even. The degree, remember, is the top power of x that turns up. It's the top power of x that turns up. That is not the same thing. You need to have every power to be even or every power to be odd in order to be odd or even as functions. So it's a stronger property. So let me just do an example to illustrate what I mean by this. This is a trap I see people falling into all the time, because you've just memorized something to do with polynomials and odd or even, and the numbers are odd or even, so you just look at the degree. But if I take f of x is equal to x to the 7 plus x squared, so that's a degree 7 polynomial. So you might say to yourself, oh, it's odd. That would be wrong. So this is degree 7, which of course is an odd number, but well, let's just feed in 1 and minus 1 and see what happens. So f of minus 1 is equal to what? Well, it's minus 1 to the 7 plus minus, I'm losing my mind, plus minus 1 squared. So that'd be minus 1 plus 1, that's equal to 0. And what's f of 1? So I'm just trying to test the condition. I'm just doing it at a really simple point, x is equal to 1, to see what happens. So this is 1 to the 7 plus 1 to the 2, which is equal to 2. So what does this tell you? This tells you f of minus 1 is not equal to either plus or minus f of 1. So what does that tell you? F is neither an odd nor an even function. Neither odd nor even, because it doesn't satisfy the defining properties. You need to have f of minus x is either f of x for even or minus f of x for odd for everything in the domain. If it fails once, it's over. Okay, and another thing to realize, so the main thing is if you do have a polynomial, you can spot if it's odd or even by looking at all of the powers. So if this was x to the 7 plus x to the 3 plus x, that would be an odd function, right? Because of the fact all the powers are odd numbers. But if there's a mixture of the two, it's going to go a bit haywire. Again, something to understand here, and this is another warning, I've already mentioned it, but this is a classic thing that people get confused about from high school. Odd or even is a much broader concept than just polynomials or powers of x, right? There are odd or even functions which don't look like those at all. So even stroke odd functions do not need to be polynomials or indeed / rational expressions. They don't need to look like that. So a real simple example. So we're going to see lots of examples of this, or some very important ones which are a very long way from being polynomials or rational expressions. Here's an example just to illustrate. If I took f of x is equal to the absolute value of x. Is this odd? Is it even? Well, let's have a check. So in this case, so as always, let's feed in minus x and see what happens. So this is equal to the absolute value of minus x, but we know that's equal to the absolute value of x. It's one of my kind of defining properties of the absolute value. The distance of x and minus x from 0 is the same, so this is equal to f of x. So the absolute value is an even function. And let me just graph it quickly for you, just to make sure you understand visually why. So what it looks like is kind of the graph y is equal to x on one side and y is equal to minus x on the other. So it's got a kind of a piecewise definition. It looks like this. So you can visually see it's even, can't you, right? Because it has reflective symmetry across the y-axis. Okay, let's do another one which is a bit more fancy. So this one really doesn't look at all like powers of x. So let's do f of x so example. Let's do f of x is equal to 3 to the x plus 3 to the minus x, shall we? Now I look at that and I'm like, oh my goodness, I have no idea. Right? I no hope I can draw the graph of this, right? It's just too complicated an expression. So we've only got one option. We've got to test directly from first principles. So let's do it. Let's see what happens when I feed in minus x. I should say the domain is everything. There are no issues with this at all because 3 is positive. We can take any exponent if I have a positive base. So what's this equal to? Well, let's take the time to do it. So this is going to be 3 to the minus x plus 3 to the minus of minus x. So what's this equal to? This would be 3 of minus x. Minus minus is plus 3x. And then if you want to be ridiculously careful about this, you can flip the sum. So 3x plus 3 to the minus x. That's a plus b is equal to b plus a. And now that's just f of x again. Neat. So this tells me f is an even function. Now, I don't know what the graph is, but I do know the graph is going to be, it's going to be pretty, right? It's going to have this reflective symmetry. Let's do a non-example, just to make sure we know how to deal with those. I'll just call it an example. So again, let's have f of x is equal to 2 to the x. Now, here's what I don't want to do. So if I was doing this without a little bit of free thought, I might try and do the same thing, right? So I'll say, okay, so f of minus x is equal to 2 to the minus x. And then I've got my kind of f of x over here is equal to 2 to the x. And I'm like, well, are they equal to each other? That minus x looks different, but maybe they're negative of each other, I'm not sure. So just because they're different looking expressions doesn't absolutely guarantee they're not equal, right? You'd need to do some algebra, right? So maybe it's the same thing just dressed up in some fancy way. So if you want to show these two are not equal to each other, or one isn't the negative of the other, which is the thing you're looking for if you're looking for odd or even, rather than come up with some sort of general reason why this isn't the same as this, just find one place where it fails. This is just the general thing about writing mathematics. If you want to show a general statement isn't true, find one specific failure, one example. So in all the above ones, we're showing general statements are true for any x. But now, I get the feeling that these two functions are not equal to each other or the negative of each other. At that point, I'm going to say, well, let's just feed in some values and see what happens. So let's try it. Okay, so let's take, so that was me kind of thinking out loud. Let's just take, I don't know, 1 and minus 1 and see what happens. So f of 1 is equal to 2 to the 1, which is equal to 2. F of minus 1 is equal to 2 to the minus 1, which is equal to a half. Okay, I think I'm cooking. So now this tells you what? F of minus 1 is not equal to plus or minus f of 1. Because 2 is not equal, or sorry, half is not equal to plus or minus 2. Half does not equal plus or minus 2. Neither of the two. So what does that tell you? Well, the defining property has failed. So it's neither. F is neither odd nor even. Function. It's quite a good idea to write function just so you don't get it confused with odd or even numbers, at least for the time being. Okay, so just to recap, we've really introduced two global properties of functions. We've introduced the concept of being bounded. So bounded below, bounded above. So bounded below was visually the statement there is some horizontal line that the graph doesn't get underneath. Bounded above, visually it's the statement there is some horizontal line that the graph doesn't get above. And then bounded full stop is there are two lines which kind of trap the graph within the strip given by the two of them. And of course you can express these precisely using inequalities. So as an example, being bounded below is the statement there exists some constant a, which is kind of giving you the height of this horizontal line, such that a is strictly less than f of x for all x in the domain. So it's a kind of a global property because you are talking about all possible values. Same thing with the other ones, pretty simple. Bounded full stop can be reinterpreted in terms of absolute values, which is very important. Being bounded is the statement there is some k such that the absolute value of x, or sorry, of f of x is strictly less than k. So that's the same thing as saying f of x is strictly between k and minus k, so it's bounded above by k and bounded below by minus k. Finally, we looked at kind of more delicate properties of a function, namely the concept of being symmetric, or symmetry properties. And the two we singled out were being symmetric after reflecting across the y-axis, or having rotational symmetry by rotation by 180 degrees around the origin. So if the first happened, it was called even, the second happened, it was odd. We took this and really carefully thought about what it meant, boiled it down to a precise definition. Even is the statement that f of minus x is equal to f of x for any x in the domain. Odd is the statement that f of minus x is minus f of x. Okay, and then we went through various examples. Be careful, polynomials are going to be even or odd if and only if all the exponents that turn up are odd or even. So it's not just the degree. So for example, down here, x to the 7 plus x squared, it's an odd degree because 7 is odd, but it's not an odd or an even function. And finally, odd or even functions are much broader than just polynomials or powers of x. The absolute value is a good example. This funny one, 3 to the x plus 3 to the minus x, even function. And finally, if you want to check something is neither odd or even, just find one position where it messes up. Virtually any choice I could make here would work, right? As long as I don't choose x is equal to 0, I think. But everything else is basically failure. So if you want to show something's not odd or even, just find one location where it fails.